Hello and welcome everyone to Know Your Scientist series presented by Ahmedabad Academy of Sciences. We are deeply honored to welcome Professor Deepak Dhar, one of the India's most distinguished theoretical physicists whose pioneering work in statistical physics has had a global impact. Professor Dhar completed his B.Sc from the University of Allahabad in 1970, followed by an M.Sc from IIT Kanpur, and earned his Ph.D. from prestigious California Institute of Technology, Caltech, in 1978. He began his illustrious academic journey at Tata Institute of Fundamental Research (TIFR), later served as distinguished professor at IISER Pune, and is currently associated with ICTS-TIFR Bengaluru. Professor Dhar's research spans critical phenomena on fractals, the dynamics of disordered systems, self-organized criticality through Abelian sandpile model, more recently models of biological growth, protein folding, and glasses systems. His remarkable contributions have been recognized with several prestigious awards, including Padma Bhushan in 2023, Boltzmann Medal in 2022, and Shanti Swarup Bhatnagar Prize in 1991, among many others. He also plays a significant role in the scientific community through editorial work with leading journals such as Journal of Statistical Physics, Physics Review E, and Journal of Statistical Mechanics, and has served on key international committees, including the Commission of Statistical Physics of the IUPAP. It is a privilege to have with him us today. Let us begin our conversation with Professor Dhar. Once again, welcome, sir.
Thank you.
Sir, my curiosity was about the Boltzmann Medal. First of all, congratulations on receiving such a prestigious Boltzmann Medal. Could you tell our audience about what this award represents and who awards it, its historical significance, and few words about Boltzmann itself?
See, physics is a very big subject.
Yes.
And there are lots of sub-branches.
Okay.
And while there is something called the Nobel Prize, which is sort of perceived to be the biggest award, it is useful to have other awards for smaller sub-disciplines.
Okay.
So there is an organization called International Union of Pure and Applied Physics, which acts like the nodal body to put together all the physics work done in all the world at an organizational level. Okay. So they make decisions. For example, at some stage people decided there should be a metric system instead of the British system or whatever. And IUPAP will decide the standard for the whole world, which everybody will then follow. Okay. So there is also an International Union of Pure and Applied Chemistry. And they decide on what is the name of a chemical, for example. So their job is mostly to uniformize the behavior or help in promoting interaction between different parts of the world and so on. So they have several commissions, some 13 of them. C1, C2 up to C13, Commission 1, Commission 13. And one of them is called C3, which is the Commission for Statistical Physics. So their job is to do the same thing which IUPA does, but only for the statistical physics part. So the one main thing which they do is every 3 years they hold an international meeting in which people from all over the world come and they discuss the progress done in the field. And they organize some awards also in this. So every 3 years they give a Boltzmann Medal and a Young Scientist Award for people recognizing some work in that, best work in that area and not recognized so far. It's not the work done in the last 3 years. It is sort of more general. It's like the Nobel Prize, you do some work in 1990 and the award comes in 22 or whatever. But, so that is the nature of the award. It is important work done in that field and awarded once in 3 years. Usually they give the Boltzmann Medal to 2 people every year. Every time it is given, which is every 3 years.
Okay. Would you like to share about Boltzmann legacy in the field?
So I think Boltzmann was a very important person as a global figure. If you want to name scientists of all times, and one of the most influential people. So he would be one of them. And I may be partly biased because I work in statistical physics. But in statistical physics, his legacy is the whole of field of statistical physics can be said to be the, something which would not have been there in the current form if Boltzmann was not there.
Got it, sir. One of your works is around self-organized criticality. For a B.Sc student, what is self-organized criticality?
Okay, so there are the aim of physics in general is to understand the world around us.
Right.
And okay, you know, there are all kinds of stuff like how does a worm move and all kinds of
Yes.
complicated things like who will win the next elections, right?
Right.
But there is some sub part of the subject which is called physics,
Okay.
which says that we will discuss these kinds of phenomena and the other things like elections we will lead to politicians. No,
Yeah.
so there is a subject called politics,
Okay.
which discusses politics,
Right.
and there is a subject called physics, which discusses physics,
Physics.
and there is a subject called chemistry.
Yes.
These are labels,
Yeah.
but they are useful labels for distinguishing between different sub areas of activity. So in physics, there is one activity which is called physics of matter, which discusses the properties of matter. You know, like started out by saying that what will be the specific heat of copper,
Yeah.
and what is, you know, so these kinds of stuff can be measured in lab,
Yes.
but there is a hope that you can also calculate them theoretically from first principles.
Okay.
If I give you the point that steel with 1% carbon, what will its Young's modulus be?
Right.
As opposed to steel with 2% carbon. I can measure them,
Yes.
but I can also calculate them theoretically.
Okay.
So the aim of a physicist is to be able to predict the behavior of the world by understanding or predicting instead of by observing from in lab.
Right.
We would like to predict the result of observations of in lab.
Right.
Okay, so when you want to predict the behavior of matter, it turns out that there is something called equilibrium matter and something called non-equilibrium. And equilibrium is easier to understand.
Okay.
So they were understood first. And you know, like if you have a box of gas and it has been kept there for a while, then you can tell what will be the pressure given the temperature and density or some such thing.
Yes.
But if the same box, the gas is undergoing turbulent motion,
Then it is.
that is harder to predict.
Yes.
And people have not learned how to predict that one. So that is called non-equilibrium matter.
Okay.
Okay, but in non-equilibrium there is some parts which are easier to understand and which are called steady states of non-equilibrium systems.
Okay. What is that?
So suppose you take some vessel, put water in it, heat from below a little bit, and let it stay.
Okay.
Then after some time, if the heat is not too much, it will come to equilibrium, where the temperature of the liquid will be a bit more than the temperature of the air.
Right.
And it will keep on getting heat from below and it radiate it to outside. So that is called a non-equilibrium state.
Okay.
So these non-equilibrium states can be simple and they can be more complicated. So like if you put very little heat, then it's just a, you know, it's slightly hotter liquid, but it just sits there.
Right.
And it can be actually predicted pretty well.
Okay.
But if you increase the heat more, then convection cells develop and you know it becomes, if you heat even more, then it becomes turbulent.
Okay.
Because water bubbles will form, all kinds of stuff. So there are many systems which are like driven systems, in the sense you heat from outside, put energy from outside, and they go into a steady state. But that steady state is more complicated and it shows lots of fluctuation with time.
Okay.
So for example, if you take climate is that Earth is going around the sun, and it goes on its own axis.
Yes.
And the sun gives it energy, which evaporates the water into air, and that comes down there somewhere as a rain, and hot and cold times and so on and so forth. But it's you can think of it as a long time steady state. If I think in terms of millions of years, then that temperature, you know, that looks roughly the same this year as next year. So at that level, it's a steady state, but it's a non-equilibrium steady state.
Okay.
In these steady states, it is important to know how much do the fluctuations occur. So sometimes what happens is that in some steady states, you keep on giving energy at a constant rate. But the relaxation when the energy has to go out, that is called dissipation. that occurs more sporadically or in bursts.
Okay.
So like I put water into the air, that is evaporation, but it comes down as rain, which comes in bursts.
Yeah.
Comes in 1 hour, and then for
Right.
20 hours or
It will
2
be
days,
nothing.
there will be nothing.
Yes.
So while the input is steady, the output is burst-like.
Right.
So these kinds of phenomena, there are many others. For example, if you take earthquakes,
Yes.
in earthquakes, what happens is that there are continental plates, and they keep on moving towards each other.
Right.
At the rate of some inches per century.
Okay.
Okay.
Inches per century.
Inches per century. And but what happens is that if they are jetting against each other, they keep on moving at this rate. Stress builds up at the place where they are colliding.
Right.
And this stress relaxes suddenly.
And
that is called an earthquake,
yes.
which occurs, once in several years.
Yes.
So it is like the phenomena I discussed before, like rain.
Yes.
And it is important to understand how big can earthquake be, or what the difference in sizes of these earthquakes.
Right.
And so people try to develop a general theory
Okay.
of systems in which the input is steady, but the output is burst-like.
Okay.
And so that theory is called self-organized criticality.
Okay.
And it was Peerbach in 1987. He gave this general idea that if you have a system which is in non-equilibrium steady state with steady drive, quite often they will go into a long time steady state which has very large fluctuations, and they will be called critical because the influence of some earthquake here can be felt thousands of kilometers away. Okay, so that general theory applies equally well to rain events as well as to earthquakes, and it doesn't address all the details, but it addresses some general features. And so that theory is called self-organized criticality, and I did some work in that area as well.
Okay. What was your favorite part about it?
Sorry?
What was your favorite part about it?
Favorite part? I think I don't have favorite parts.
Okay.
It is, there was one mathematical problem at one time which I could solve. So I was happy to have been able to solve it. If I hadn't solved it, somebody else would have done it.
Okay.
Okay. So it is not so much a favorite. It is some parts of the, we look around nature, some things we understand, some things we don't understand, and some things with some effort we can understand a bit better.
Right.
And at any given time, there are still unsolved problems.
Yes.
And those are the interesting ones. And the ones which have been understood, they are still interesting, but not for a researcher for further work.
So no favoritism.
No. There are some problems which are more interesting than others to me at any given time.
Got it, sir.
But that is a personal preference. It is not universal for everybody.
Got it. Yeah. Talking about phase transitions,
Okay.
you've explored various aspects of phase transitions.
Yeah.
Could you elaborate on the types of systems where you study these mechanics? And are there surprising examples beyond the water, ice, and magnetism scenarios?
Yeah. No, so the problem of phase transitions has long history, about 200 years.
Okay.
Because it is a very spectacular phenomena. Like you look at ice and you heat it up and suddenly it becomes water.
Yes.
So this thing is spectacular. Everybody can see it. It's everyday experience. Can we understand it?
It's a question.
Whatever that means.
Yes.
As a physicist, can I understand melting? And it turns out that that's actually not well understood, and it is very surprising.
Okay.
Okay, so let me, for an undergraduate student, let me explain it like this: that if you look at ice at minus 0.001 degree centigrade, it is ice, it is regular solid, all atoms are vibrating with some energy, but you increase the temperature by just a little bit so that it is above the melting point by 1 part in 10,000.
Okay.
And everything melts and it becomes a liquid.
Right.
The energy per particle has only changed by 1 part in 1,000. And how can that lead to such a big effect?
Right.
So that's the question. And of course, people have studied this problem for a long time. It's called a first order transition. So the fact that phase transitions occur is a little bit surprising, but this is understood by now. People realize that it occurs because of cooperative effect of lots of particles.
Okay.
So what happens is that each atom jiggles a little bit more,
Okay.
but in the process of jiggling, the other person is also jiggling a little bit more. And so it may happen that everybody can, the atoms can become liquid-like in the sense they move all over the place,
Yes.
while in the solid they are all confined, because each one is confined by the neighbors. The neighbors are keeping you in place, and they are being kept in place by their neighbors. And this effect suddenly breaks down at one temperature. So it's the effect of cooperative phenomena, कहते हैं इसको generally. So it's a cooperative phenomena, effect of many particles together. That is well understood. Some parts of the details of this were still not well understood even now.
Okay. What are those parts?
Uh, so let me say that for water, actually there is a lot of study.
Okay.
But I would say that at the level which is general enough, for I don't want to study only water. I want to study alcohol also melting and
Almost
so on.
everything.
All other materials. The general theory of melting is not yet known, in spite of so much work. So what happened was in 1970 there was some study by Ken Wilson. He is a very famous statistical physicist. He got the Nobel Prize. So he realized that if you have phenomena which are critical phenomena, where near the phase transition the correlation length becomes infinite, then they can be understood well. So people started studying these critical phenomena, and there is a lot of work in the next 50 years. But much more elementary phenomena like melting, which is not critical, it is a first order transition,
Yes.
are less well understood. Okay. So my thesis work was also actually on melting transition. We didn't solve the problem.
Okay.
So, but I tried to understand it, didn't succeed fully, but we did, some one step in that right direction. So that was, so I would say that phase transitions are very common. Then people find that actually there are also non-equilibrium phase transitions, which in many ways look very similar.
Right.
Okay. So some of the theory can also be applied to non-equilibrium systems, and some of the theory would not work. Usual way to explain the phase transitions is to calculate equilibrium phase transition, is to calculate the partition function. And when the partition function shows some funny behavior, then it's a phase transition. Yes. In non-equilibrium, there is nothing called partition function. So the step one does not allow you to work. So you have to develop some other ways to deal with it. So that's the problem, and that is the interesting field for which a lot is known. Okay. But not everything is still understood, and it's still an active field of study.
For someone who's starting a PhD, who wants to solve this problem inspired by this video, how would you guide them about solving this? As you just mentioned,
I would say that one can certainly identify or convince a person that this is an interesting problem.
Okay.
Okay. Yeah. That doesn't require great convincing. How to solve it is a different question. Right. That is much more difficult, and if it was easy, I would have solved it already.
Yeah, of course.
So there is no answer to that one. Yeah. You should try. You may succeed. If you succeed, you will become rich and famous. If not, okay, you can still manage. You can do some intermediate stuff.
It was about the part that you mentioned, like there is a lot of work to be done in next 50 years. So, if you could guide someone to the exact problem in even more detail about the melting.
No, so I would say that there are thousands of interesting problems to study.
Yes.
And so there is 1,000 students can do PhD on different problems. I cannot identify one problem that all the 1,000 students should work on that one problem.
Got it.
It will be kind of stupid thing to do. Yeah. And we are very happy or lucky that there are large number of interesting unsolved problems, and one can study any of them.
Yes.
And they don't even have to be in physics. If you want to solve some interesting problem in biology, that is equally interesting.
Right.
And there are interesting problems in stock market modeling or stock markets. Yes. If you know some nice way to make money in the stock market, that's very good. Okay. But it turns out that sometimes the techniques people have used to understand physics can also be used to understand stock markets. Maybe, may not be, but So the point is, one should try to keep an open mind and understand what's an interesting problem and study them. It's not necessary to ask your supervisor what problem should I work on.
Great. So talking about stock market, how does have you ever tried to understand the pattern, analyze things?
No, I worked on the stock market, but I don't spend real money.
Of course, yeah.
We don't have too much in the first place,
Right.
and it's a little bit of risky proposition.
Okay. So just asking from someone who's not even having a science background.
So, for example, as a physicist,
Yeah.
what we realize is that a system of stock market is a set of agents which try to buy and sell stock every day.
Right.
So they are like interacting particles. They interact with each other,
Okay.
and what happens depends on these interactions.
Yes.
Now, it turns out that there are some external parameters which decide what happens.
Or how the interaction happens.
How
Maybe its bias is more, the external parameters.
So, how the interaction happens, they go to the market and they offer a price,
Right.
that I am willing to sell this stock at this price, and if somebody wants to take it, then they take it. So this is the usual market mechanism.
Right.
But how do I decide what price I should offer?
Right.
This is the question they ask. Or if this is being offered, should I buy or not buy? This is the kind of decision you have to make.
Yes.
And the point is, my decision depends on the decision of other people.
Okay.
If a lot of people want to buy, then the price of stock goes up.
Yes.
If it goes up, then more people want to buy. So it can go up even more. So, there is a cooperative feedback effect in this as well, which is actually in some ways similar to the cooperative effect seen in melting transition or some such thing. So that is, a physicist will identify these common patterns. And we'll say that the theory of melting can also be applied to the stock market, which is true or correct, but not 100% true. It catches some part of the phenomena, which is all it does, and that's what all it was aiming to do. It was not aiming to explain everything. Sometimes the student have a feeling that I have to explain everything, but it's not necessary. If you can explain 10%, that's good enough. Okay, you can make a lot of money if you are successful 60% of the time as opposed to 50%.
Yeah.
Right, like that.
Right. Got it, sir. Equilibrium versus non-equilibrium statistical mechanics, as we were just discussing. What are the key differences between equilibrium and non-equilibrium stat mech, and why is the latter considered a frontier area?
Okay, so the key difference is that in equilibrium stat mech, the basic principles are actually well known since the time of Boltzmann.
Okay.
So it says if there is a system in equilibrium, it has these many configurations possible. Each configuration occurs with this probability. You know the probability of different configurations. They are given by some formula, Boltzmann formula. And then you just have to calculate the behavior based on this probability. This behavior is hard to calculate. That's a mathematical complication.
Okay.
The problem is well posed.
Okay.
In non-equilibrium, that step which says that we know what we want to calculate is not so clear, or it is not as a the different configurations occur with what probability is not known, and it varies from place to place and system to system, and there is no general formula like exponential minus beta h which works in every case.
Right.
And so that is why it is considered an open problem. And since we want to understand it better, then people work on it and see if it can be done.
Okay. Talking about cosmological connections, some physicists say that the universe itself might be described as a non-equilibrium statistical system.
No, that should not be considered. Some people think like that.
Okay,
it is obviously true. It's a non-equilibrium system.
Okay.
The stars are exploding.
Right.
The universe is exploding. It's not an equilibrium system, whatever it is.
Yeah.
So it's non-equilibrium. Then you can ask, can I understand some properties of this non-equilibrium system? And maybe if I can. If I can understand how a very hot gas in a small region explodes to bigger one, then I can guess that maybe something similar occurs when galaxies explode into a bigger one. At that level, there is a similarity, and it is there. You cannot really deny it.
Of course. Would you like to share any such phenomena right now about taking non-equilibrium systems and understanding universe through it?
So for example, let me discuss it just for a few minutes. The work which I did, for which this one self-organized criticality.
Yes.
There is a model of self-organized criticality called the sandpile model.
Yes.
So you take a lot of dry sand and take a table and pour sand slowly. It forms a pile,
Yes.
which is usually a conical pile.
Yes.
And then you keep on adding sand grain at a time.
Okay.
Then sometimes the grain will go and sit on the top of the pile.
Yes.
Sometimes it causes an avalanche
Yes.
and a lot of sand comes down. And so it is an example of a slowly driven system where the relaxation occurs in bursts. Because you are adding pile at a constant rate, but the output is a burst-like. So can we understand the behavior of just a sand pile with slowly added sand and avalanches occurring to dissipate the particle? So that was the model. And so there was a mathematical version of the model which when I managed to find some mathematical structure called Abelian groups which can be used to discuss this model.
Okay.
So that was the work which is useful because it was one of the first examples where you could actually analytically track these models. The model was defined by Peerbach,
Okay.
but he studied computer simulations. My work was more sort of analytical, which reproduces the same results, but I like to think that it produces better understanding.
Okay. Got it, sir. Talking about the same, how much of your work involves computation, and what numerical or analytical methods would you be using?
Yeah, so it certainly involves some numerical simulations. I actually a lot of it is simulation, but I would say that we would not like to stop at simulation. We would like to understand what the output of the simulations is.
And
Okay, so that step called understanding is different from just running a program and getting an output.
okay, so how do we understand that?
That is actually non-trivial and it's not codified as a standard procedure,
Okay.
SOP. So I don't know how to answer that one. It is like saying that, okay, you see something in front of you, your girlfriend, let us say, can you tell what she will do tomorrow?
No.
Okay. Sometimes with some experience you can tell, you develop some rules,
Right.
which are approximate rules, which will tell this person does this, and if you do this, then they will do this. Physics is like this. They say that if this particle comes, they collide, this will be the output.
Yes.
It's prediction at some level. Sometimes you cannot make exact prediction, then you make approximate predictions.
Right.
Sometimes they don't work.
Sometimes they do. Got it, sir. We are generally introduced to statistical mechanics of particles. Would you like to talk about statistical mechanics of fields?
Yeah, okay. So it's actually the same thing said in different words. Let me give an example. Suppose I take ice was our example.
Yes.
Ice molecules sit in a solid. So I can think of them as molecules which are acting with nearest neighbors, let us say, and there is some interaction and they jiggle.
Yeah.
This jiggling can also be described by harmonic spring model. There are atoms, masses connected by springs.
Yes.
So I can describe them as interacting particles with spring interactions. But I can also describe it as a lot of sound waves because there is a stretch string. The vibrations can be expressed as sum of normal modes. So it has some amount of motion in this mode, some amount of motion in this mode. So once you discuss it in terms of waves, then it becomes an interacting waves problem. Or let me say another way, if you take a lot of these particles, you can say each particle has a displacement. And this displacement changes from place to place.
And then we are
field as a function, the displacement as a function of position is a field.
Okay.
So it is called a
So are we considering that displacement as the amplitude of the wave?
Yeah.
Okay. Got it, sir. Would you like to talk more about this? Fields.
Fields. So for example, electric field, which is what people study, is also there is a function E, which is a function of space and time.
Yes.
But if E at one place is known, the E at the next place is close to it. Or so E is a smooth, continuous function of position.
Yes.
Okay, so this condition gives rise to description of electromagnetic field.
Yeah.
And there is a Hamiltonian for the field. Given a field configuration, there is an energy. and you can discuss even the equilibrium state mech of electromagnetic field, which will be like field inside a cavity. If you have a cavity at a temperature, then inside there are all kinds of waves, fields, or photons come in, absorbing, emitting, and so that will be the statistical mechanics of
Fields.
either particles called photons or fields called waves. It's the same thing, it's just words.
Got it, sir. In undergrad level, or let's say even master's degree, some of my friends, as well as me, consider statistical mechanics a really difficult thing to understand.
So I think quite often the difficulty is not with the subject,
Okay.
it is my prior exposure. So like when I was young, I was very scared of doctors and injections.
Right.
Okay, if you think about it, the injections are not so painful and they are not so scary, but depending on your, when I was a child, I was scared. I mean, it cannot be helped.
Right.
It's a psychological issue. When I was taught the subject first time, I was not taught it well and I didn't understand it. And I think it is a problem of the subject, but it was actually not the problem of the subject, it was the teacher. Slightly different example, but let me give it.
Yeah.
My daughter, she was 1 year old. She used to go to kindergarten. Just before going to school, she would develop strong stomachache. And we were wondering, what's going on. It was her teacher she was scared of. That caused the stomachache. I'm not saying stomachache was not real.
Right, but it was psychological.
It was psychological. So I would say many of these difficulties are psychological. It is also true that all people don't have equal ability in mathematics.
Right.
So we know that at the high school level, 50% of the general student population are not comfortable with high school level mathematics.
Yes.
Okay.
Yes.
So I would not like to say that people who don't understand mathematics well are lower class. Okay, because some of them can be painters. I don't know the mathematical skills of Lata Mangeshkar, but she's great in her own way, right?
Yeah.
So people can do very good work, but not have strong mathematical skills. But if you want to work in physics, maybe it's not easy to do it without having some mathematical ability.
Right.
So for some people, it will be a difficult subject. They should do something else. But for a large number of people, it is not so difficult. There are thousands of students who can do very well in StatMech.
Right.
So I used to say that Chinese, it's a very difficult language. But if 1 billion people can speak it, it cannot be so difficult.
Right.
Right? It's like that.
Okay, sir. If we want to make some changes for the people who are good in maths in the education system, let's say around high school or in early college times, how can we help them overcome this psychological barrier?
That is, I think it's very difficult in practice because what it requires is a large number of well-trained teachers. If the teacher can explain something to you well, it will be done. But what it needs is better teacher training.
Got it.
Okay.
Yes.
It is hard to do, but it can be done. It is not like it cannot be done. If there is political will, then it can be done.
Okay. About current research trends, what are some exciting directions in statistical mechanics which are emerging and you might be excited about them in near future?
Okay, so in statistical, I would say that there are 30, 50 directions which are emerging and which are in. And I don't have the ability or stamina to work on all of them.
Of course, yes.
So I work on one or two of those interesting problems, or what are interesting to me. Maybe everybody doesn't share that view.
Yes.
But there are many other interesting problems which are being studied by other people. In general, the application of statistical mechanical ideas to other disciplines is a very important area.
Part of it, yeah.
So people apply it to biological problems, biophysics. They apply to geophysics, earthquakes, climate sciences, even stock markets.
Yes.
I was told that I should say something about the cosmos.
Okay.
because the students are interested in the cosmos. So let me start by saying
Okay.
that actually there is a small story which I would like to share, which was told to us when I was in Mumbai by Abdul Salam.
Okay.
So he was telling that there was school teacher in Jang. He grew up. He was born in Jang, and the story is about Jang. So he said there are these four fundamental forces in physics. All of us know about gravitation.
Yes.
In Lahore, there is also electricity. And weak and strong forces, they occur only in Europe. It's not fully right,
Yeah.
but it is not fully wrong.
Okay.
You see, if the electricity is not there with you, then having a big theory of electricity doesn't make much sense.
Yes.
It doesn't relate to our experience. Okay, so I would say that while I find that the cosmos is interesting, I cannot relate to it much myself. I'm like this person who doesn't have electricity at his home and you are teaching him electromagnetic theory and I don't understand. So what happens if two pions collide with each other at high energy? I don't know what's a pion. It's not part of my experience. That was my feeling.
Okay.
As a student, that was my feeling. And so I never got interested in high energy physics.
Okay.
And similarly, there are all those stars. Some of them are actually galaxies, but they look like stars to me. I cannot tell the difference.
Right.
I don't know if in a galaxy there are 10 to the power 9 or 10 to the power 12 stars.
Okay.
I have no feeling for these numbers. It's, one of them is right, and maybe there are big and small galaxies or something. But I was not getting excited by understanding the structure of galaxies too much. Now, of course, I'm a bit wiser. So I realized that some of the things I know can be used to understand some of these things at some level. And so you live and learn. But at any stage, there is a stuff which you don't understand well. And cosmology is one of those things.
Okay. Got it, sir. Would you like to tell something about are we building enough capacity and attracting young talent to the field, especially statistical mechanics?
I would say that there are two parts to this. One is the quantity and one is the quality.
Okay.
So I think the number of Ph.D. students working in science in India now is reasonable. We can increase it by a factor 2, but we can also keep it the same. But what is required is to improve in the quality. That is much more important than just increasing the quantity. Sometimes one cannot occur without the other. Like, suppose I'm in Olympic Games. People always used to say that why there are so few Indian medalists.
Yes.
But if you don't have sports facilities in the colleges and universities,
Right.
you cannot get
quality.
the gold medal in the Olympics either.
Right.
So if you have large number of base, then only you can expect something to be bigger. To that degree, it is very important to have a large base of large number of people and adequate support in science.
Got it, sir. Talking something about mentorship and learning, many students find statistical mechanics challenging, as we just discussed. So, could you recommend some good books or learning resources?
Yeah, so I find one book, Rife, Berkeley Physics course.
Okay.
It's a very excellent book as an introduction. It was written 70, 80 years ago.
Okay.
It still is perhaps, according to me, the best introduction.
Okay.
It doesn't need to be rewritten.
Okay.
There are sort of other books which are comparable. They cover slightly more material. So Rife himself had written a bigger book.
Okay.
But then he wrote this Berkeley Physics course in which he deleted some of the chapters in the original book.
Okay.
So it's as small as it can be. So it's the first book which you should learn. After that, there are other books like Patharia, Kardar, and I like Chaudhary and Stauffer very much because they have a lot of historical anecdotes at the end of the chapters, which are sometimes missing in some. And then you miss out on the sort of understanding of how science actually happens.
Hmm.
Sometimes you can think of them as stories, but sometimes they can be much more than just a story.
There are many books which are in story format and are very attractive.
Huh.
Is that?
So it turns out that we can understand stories much better than we
And-
can understand a mathematical equation.
Even we can remember them.
You can remember them and you understand them without training.
Yes.
To understand an equation, you need some training.
Yes.
But interestingly, so science and music, I would say, are similar activities.
Okay.
Creative, so you want to do something different, new, whatever. But music people are able to relate to much more easily than they are able to relate to science.
Right.
Okay, so if I write one nice music piece, I can expect million hits.
Yes.
If I write a nice paper, okay, 100 like that.
So are you into music?
No,
From that question.
actually, I'm not able to do much.
Okay. Yeah.
But I'm struck by the fact that people can appreciate good music.
Okay.
And they can tell that this is good and this is bad, and this is sort of not just a random choice.
Okay.
A lot of people will agree that this is clearly better than this.
Right.
In science, if I give you two papers
Yeah.
to a general public, they will not be able to tell this is a better paper than this. So that discrimination is not so easy to make in one case, and I wonder why.
Okay.
Because our brains are wired this way.
Okay. Sir, I would like to know more about your childhood. Were there early indications that you would be a theoretical physicist or scientist?
Okay, so early indications of being a that would be very difficult. There is no such, there are in small child you cannot tell he will become a physicist.
Like school.
But certainly, what can say is that some people have some mathematical ability.
Yes.
So you can get 100 out of 100 in mathematics in school exam.
Yes.
And then you are better at math than some other students. This much is true.
Yes.
So I was better in maths than some other students. There was some general mathematical ability.
Okay.
Then you can use it to do whatever you want. So I found that, okay, when learned about a lot of mathematicians and physicists and other people, and I found that I was more attracted towards physics problems than mathematics problems.
Okay.
Though it is somewhat in between.
Right. So, were there any mentors or any specific event that would have played a pivotal role?
No, so I have had lots of mentors, not just one.
Okay.
In various stages in my career.
Yes.
I think the one I have sort of cannot avoid mentioning is Feynman.
Okay.
Because he was at Caltech when I was there.
Correct.
And he was also I was a tutor for his course.
Okay.
And he was also in my Ph.D. thesis committee.
Great.
So, but more than that, I was able to once watch him when he was teaching other people.
Yeah.
And so he had a attitude which was that too much of excess formalism is not good, and you should have some understanding with quote marks.
Please elaborate that.
So I think it is difference between writing some lot of gobbledygook and understanding.
Okay.
So his story is that he has told this story to other people, and I'm just repeating it.
Okay.
He said that there is this bird in Japan, and the name is Chakwatoku, and in Swahili it is called this.
Okay.
And in something else it's called this,
something else.
Latin name and something. He says if you know the name in 30 languages, you don't know anything about the bird.
Okay.
You should instead learn what
I've heard this somewhere.
Yeah. So because he used to repeat it again,
Yes.
because it was important point for him to
Right.
make. And so if you write some very complicated equation or fill pages of algebra with G-mu kind of symbols,
Right.
I say, what are you talking about?
Right.
So I sort of step back and say, suppose I am a 10-year-old or I'm a high school student, do I understand what's going on?
Right.
If I don't understand that at that level, then I feel that I haven't understood.
Got it, sir. Sir, I just now
Okay.
came to know about Feynman. So,
Hmm.
would you like to share how was it working with him?
I mean, I was not working with him. He was in
In a
the
way, he
department,
was there, right?
so I could watch him,
Okay,
which was good enough.
right.
I can say that, of course, he was great, and I'm nowhere near there. If I'm 1% of what he is, that is good enough for me.
Great.
Like that.
Yeah.
And but he did help shape my attitude towards research in general.
Okay.
So that is what I can say.
Great. So,
Even presenting the research to ordinary people. So there is another story here.
just a second. Sorry.
There is another story he used to tell everybody. He said he was going through some airport and some reporter caught him, and so he was saying that. So Feynman was just complaining to the person. He was saying that when you go through the airport, all kinds of people just catch up with you and say, Professor Feynman, can you explain your theory to me?
Yes.
And this reporter laughed.
Okay.
And he said, you should tell him that if I can explain the theory in 5 minutes, maybe it didn't deserve the Nobel Prize.
Of course, of course.
So they just laughed and they went away, but he kept on thinking about it. And 2 days later, he called up the reporter again. And he said, no, I was wrong. If you cannot explain your work to a high school student, you don't really understand it well enough.
High school student in 5 minutes.
No. If you cannot explain your work to high school student,
You have not
you
understood
don't understand it yourself well enough.
Right.
Okay, so that is, if your understanding can be brought to that level such that other people can understand it equally well,
Right.
that is true understanding. And if you can just write a paper which is 100 pages, which nobody has read and nobody wants to read, that may be very, very erudite,
Right.
but it is not the same thing.
Okay. Got it, sir. What would you like to quote about this beautiful ICTS campus?
Oh, I think it's really very pretty, and
Right.
I am very lucky to be here. And I think sometimes I know a lot of people who come from outside. Sometimes they feel that the scientists are a pandered community, and they are able to enjoy some such thing while I have to live in my grungy flat in Bandra.
That is the thing with such a beautiful campus, and it looks like it is designed, right?
Yeah.
The
Of
board
course,
and
it is
there
designed.
designed for
It is
scientists itself.
designed.
Yeah.
So while it may look like it is a lot of privilege,
Yes.
I think it is useful for the country to have a few places
Of course.
like this,
Yeah.
because in the end the output is
Comes from there.
commensurate or should be commensurate with the input. If one just sits here and only enjoys the scenery and lazes all day, that would not be the it. So one should look at what is the output of the institute.
Of course.
And if you look at the annual report or whatever, you will see that it is actually well worth the money spent.
Yes.
And these things are incidental, and they help. Actually, they help in the work, because when I talk to people, they say that I ask them, why aren't you doing better work than you are doing? So they say a lot of my time is spent in doing trivial stuff, like buying bread for my family and bringing children from office. So they say that it takes a lot of time and energy, and you don't have enough energy to do other things.
Right.
So the idea is that if you can make those things a little bit easier, then you can do these other things a bit more better.
This campus helps that part.
Yeah.
So you've also been to Caltech, and there are innumerable institutes you've been to.
Right.
How was your experience there? And
it was great. I mean, I think I would not be where I am if it was not at Caltech.
Okay.
Of course.
Yeah.
It was a formative years.
Yeah, of course.
So if, whatever you learn during your PhD, you have to keep it and grow with it. But if you don't get a good PhD, then you don't have enough training to do better.
Of course. It is, I would say, or quote it like that, that it is a privilege for us that scientists like you are returning to India.
Okay.
So how would you look at that matter, returning to India?
Okay, so my own choice was personal choice.
Yeah.
And I didn't actually work in USA, but I was just a student. As soon as I finished my PhD, I came back.
Right.
Okay. My choice was kind of personal choice. I have only son in my family, so I have
Get that.
parents. What about my father was going to retire 2 years after I finished PhD or something. So it's like that. So it's a personal choice,
Got it.
and I have not regretted that choice because I don't know what I would have done if I was in the US. I tried for one or two places,
Okay.
didn't work. Then I just came back.
Great. Yeah. Okay. Talking about childhood, as you just mentioned that there are not really early signs, right? But in school or let's say in college, there might be something, some experiment, some theory, some equations that might have fascinated you, or that played a role. That okay, when did you decide you're going to be a scientist?
No, so actually, my father was very wise person. He encouraged
Okay.
me to study generally science.
Okay.
So instead, small things like 1, 2, 3 Infinity by George Gamow. There is
Okay.
a small book,
For
and there are a
children
lot of
specifically.
popular science books
Yes,
for
yes, it is.
at children level. Initially it was a lot of work for me to get to learn the English,
Okay.
but one eventually learns it, and
Yes.
then it works better. So he developed some taste for in
And you.
encouraged me to develop taste for science,
Right.
and he also said that IAS is not the only thing in life,
Okay.
which is not typical for many
Right.
parents.
Right. Right. Got that.
So
What was the physics department of Allahabad University like? Would you like to share any memories or any professors you found in
okay, so I was not very happy when I was in my B.Sc.
Okay.
In general, the atmosphere in the university was not very exciting.
Mhm.
There were one or two very good professors, but we used to interact very little with them. We just go and listen to the lecture and come out and study on our own.
Right.
But actually, I had one professor called Bipin Kumar Agrawal, who was used to lend me some extra books beyond the text material.
Okay.
And he used to be a painter, he used to
Right.
paint himself and stuff like that. So I think because of all these interactions, I was able to continue and develop my interest in science.
Right.
The university environment at that time was not very good
Okay.
on the whole. I think it was sort of not the time when Meghnad Saha was there, it's much later.
Right.
And most of the best students in the class
Mhm.
wanted to appear for IAS exam, and that was
Okay, that was the goal of
that was
most
the
of the
goal of
students.
life.
Right.
And I was not in sharing that goal, and
Right.
didn't have too many other students who were similarly inclined.
Right.
So I was very happy to go to Kanpur, which was much better
Right.
intellectually.
Okay.
Then I went back to Allahabad once, actually in the middle of my M.Sc. And one of my professors in Allahabad was asking me, how did you like the stay here?
Okay.
And I told him that, oh no, first he asked me, how do you like Kanpur? So I said, oh, it's very nice and I like it very much. And so I very lively. तो उसने कहा और यहाँ पर क्या था क्या यहाँ पर कुछ मरा मरा था so the point is not to blame something, but it is true that in many places the students don't get adequate environment for growth.
Okay. Right.
Which I think was true also for me. And so I would say that in those 2 years I learned less than I could have learned.
Okay.
And that may be partly my fault, but it's also partly the fault of the system, which does not allow people a lot of freedom to do what they want, or it has a very rote syllabus.
Okay. Yeah. Talking about your journey to Caltech, what led you to pursue PhD at Caltech?
Actually, when I was in M.Sc in Kanpur, everybody was applying abroad for PhD.
Okay. Right.
So I followed the crowd and I did the same.
Okay.
I applied to several universities.
Mm-hmm.
Luckily, I got admission to
Caltech.
several of them, 6.
Okay. Great.
Then I had to choose.
Yeah.
And I have no real data point for choosing.
Okay. You do remember all 6 of them?
Yeah, but let us not
Okay.
make a list.
Fine.
So, what I decided was just a name.
Hmm.
This name seems more familiar,
Okay.
and a large number of very eminent people.
Yes, sir.
There were some 20 Nobel laureates at Caltech at that time.
Yes.
Living in
Okay, there.
something like that.
Right.
Maybe the number is not fully right,
But
pretty big.
yeah.
And so I'm sure some other universities can also have similar score.
Right.
But I didn't get admission to Harvard.
Okay. Got it. How was the transition like?
Actually, the transition was not so hard.
Okay.
So when I was in Caltech in the first year, you have to take a lot of courses.
Okay.
Quantum mechanics, mathematical physics, and electrodynamics. And I found that those courses were kind of repeat of the courses I had already done at Kanpur.
Okay.
So Kanpur had prepared me well.
Great.
For this kind of study. So it was not so hard. I think the overall attitude to study, etc., of course, is different, but that you imbibe slowly, and that doesn't come in one day.
Great. So many physicists, after some of the research, they have some strong opinions on philosophy. They start following a philosophy.
Okay.
Do you do the same?
I think it is difficult to live through life as a thinking person without having some philosophy or the other.
Right.
What I have found is that I used to actually read lots of philosophy books.
Okay.
But I find that, now if I try to remember what was written in that book, it is very hard to remember. You can read a 300-page book on philosophy,
right,
and later ask, what did I learn from this? They have very complex argumentation, and it confuses you more than it helps you. At least the books I read.
So, is it better to develop your own philosophy?
Of course. Or developing your own will take lot of time.
As in just for your life.
Yeah, no, I understand. It is like in reinventing the wheel.
Yeah.
The wheel has been invented, that philosophies are already there.
Right.
You should understand them and adjust them to your needs.
Okay.
Sometimes you can say that this doesn't sound right, this is partly right.
Right.
So if you use evaluative criterion for philosophy, it comes out much more palatable, and you can use other questions like, okay, I have read this book, how does it help me live my life?
Right.
Okay. So I have read existentialism or I haven't read existentialism.
Okay.
Does it change my attitude to things around me? If it didn't change, then reading that book didn't matter. Okay. Right, that's the point. I think nowadays the teaching of, I have seen some new textbooks on philosophy which are much more better and they express it in common terms. Right. In old days they used to be just quibble about words. Yeah. So let me just, because this is for other students, let me explain that point. So there is a story about two seminary students. Okay. They were seminary is this European school for monks. Okay. They are trained to study philosophy or religion later. Okay. And these were very studious people, and they were studying all night, discussing nature of good and evil. Good and evil. Okay. And in the morning, one of them said, now I understand, your God is my devil and my devil is my God is your devil. Yeah. And so the point is that you can have long discussion, but it's about words. Yes. So when I say devil, I have some meanings attached to this word, and that guy has a different set of meanings attached to that word. Okay. And most of the time they are quibbling about the names of things, which is an irrelevant discussion. Okay. So how should the philosophy be? So you ask me some philosophical question and let us see if I can do. Okay. What I have gone through, I've gone through a really narrow space of that. It's about our existence is absurd, and to make it feel like there is some maybe find purpose of our life. There is nothing like that. It is total absurdness. And okay, very good. No, so as a physicist, one truly believes that there is a universe. All these points are also disputed in philosophical discourses, but we are saying there is a real universe. Yes. Okay. And there are galaxies, and we are one small part of one small part of one small part of something. Yes. So the fact that if I live or don't live will not matter much to the universe should be accepted as a fact. Okay. And if I want to say that, the God is bothering particularly about me and making sure that I'm doing something right,
Yeah.
God will have a lot of worries because He has too many people to worry about.
Around 9 billion.
Only human beings, and there are all the worms and birds
Yeah.
and other animals.
Right.
So does God worry about them or does God not worry about them?
Okay.
Okay. So the fact that our existence is not meaningful at that sense should be accepted as a fact. But I can assign meaning to my existence in some other way. Okay, it doesn't have to change the cosmos.
Right.
But it can change my surroundings.
Cosmos
it
around
can make my wife happy or
Right.
my father happy or whoever. Then I can make meaning to that. So the word absurd
Yes.
and the word meaningful, these are what we are discussing, and
Yes.
they have different meaning for me. It can be absurd in your sense, but
Yes.
still meaningful in my sense.
Right.
Okay.
Got it, sir. Any concluding thoughts for our viewers or early research career scientists?
Yeah, no, so actually there is one thing which I feel very strongly, which I would like to
Sure.
tell your other viewers.
All the viewers.
Is that in India, the students who come for physics
Hmm.
quite often seem to come with the idea that the more complicated and abstract theory, the more attractive it is. Okay.
That's an idea.
So why do I want to worry about the cosmos? Because this is the biggest thing that I can think of. Or why do you want to worry about the Planck scale? Because it's the smallest thing I can think of. But they don't worry about the physics at the human scale or life at the human scale. They don't relate to what happens to the galaxy, to my life.
Yes.
And I would say that okay, those problems are interesting, but problems at everyday human scale are also interesting.
Yes.
And they should not be. One should not take the attitude that only those problems are interesting. Unfortunately, that is the view which seems to be following some amongst Indian students more than amongst other students.
Okay.
But like if you want to do anything, you want to do string theory. The students have this perception.
Yes.
And they are based on some, they don't know what is string theory really. But they still think that is the best thing in the world.
Okay.
And I don't know why they feel that way. It is based on some hearsay, based on some other people saying this. And I'm saying it doesn't relate to their own experience in any way. And I would say if they try to find something which relates to their experience, their life will be much better off and they'll be happier person on the whole.
Right. Got it. So that was great. We can say that this could be a part of the philosophy of you that we were talking.
Yeah.
That this could be like be authentic.
Yeah.
That could be a thing.
One should try to make your life meaningful in the sense that it makes a difference to somebody.
Yes.
Okay. Or to some set of people or a whole nation or whole mankind even.
Yes.
Okay. So maybe we don't get there,
Yeah.
but we can try.